Good day students. Today we will be discussing about the proof for the sampling theorem. In the previous class itself, we have seen that the input signal x of t and the del impulse train del t of t are presented to the sampler to produce the corresponding output x cap of t. So, we will go for an analytical expression where we can perform sampling to obtain x cap of t or the signal x of n, and hence the reconstruction of the signal x of t from x cap of t. The equation goes like this: x cap of t equal to x of t multiplied by del t of t, which is nothing but every sampled instant of x of nt multiplied by the shifted version of the signal, impulse signal del of t minus nt. So this can be easily verified by observing the signals x of t and del t of t. We know that the del t of t impulse train is a periodic signal. Hence, the trigonometric Fourier series of del t of t is given by del t of t equal to this expression. This expression can be easily verified if you refer to the Fourier series of a periodic train of impulses. So here 1 by t into 1 plus 2 cos omega st plus 2 cos 2 omega st, and it goes on till infinity, where omega s is nothing but the sampling frequency in radians. So omega s is equal to 2 pi by t, which is equal to 2 pi fs, where fs is a sampling frequency in hertz. Therefore, so having derived an expression for trigonometric Fourier series of del t of t, we can represent x cap of t or the discrete time version of the signal x of n. It can be represented as x of t into del of t. So del t of t is multiplied by 1 by t, giving rise to this expression. In order to study about how the signal can be recovered after sampling, we need to analyze a signal in its Fourier spectrum domain. Hence, this x cap of t, which represents a discrete time signal, can be analyzed in Fourier domain. To do that, we have to find the Fourier spectrum of this entire expression. So proceeding, x cap of omega is the Fourier transform of x cap of t. So x cap of omega is a Fourier transform of x cap of t. So rewriting the expression again from the previous slide. Now Fourier transform of x cap of t is equal to we need to find out the Fourier transform of each and every term in this expression. So Fourier transform of x of t is given as x of omega. Similarly, Fourier transform of 2 into x of t cos omega st is given as x of omega minus omega s plus x of omega plus omega s. This can also be easily understood by finding out the Fourier transform of cos omega st, which gives shifted versions of the spectrum. So this spectrum represents x of omega shifted by minus omega s and plus omega s. That is, this original spectrum x of omega is shifted by minus omega s and plus omega s. Similarly, the third term, Fourier transform of 2 x of t cos 2 omega st, when found out, will give x of omega minus 2 omega s plus x of omega plus 2 omega s, which is nothing but the spectrum x of omega shifted by minus 2 omega s and plus 2 omega s. This goes on up to infinity. So summing the entire right hand side of the expression can give x cap of omega equal to 1 by t, and summing all the Fourier transform gives from n equal to minus infinity to infinity x of omega minus n omega s. This is the reason why we get the Fourier spectrum of a sampled signal with repeated versions of the spectrum. So this expression clearly states that the spectrum x of omega, actually the spectrum x cap of omega, the spectrum x cap of omega consists of this fundamental x of omega, which repeats periodically with period omega s. You can see that the central is 0 and then we get here omega s, and again here it is 0, and on the left hand side it is obviously minus omega s. So this spectrum x cap of omega for the total one consists of just the actual x of omega repeating periodically with period omega s equal to 2 pi by t radians per second, or in terms of frequency in hertz, it can be told that Fs is equal to 1 by t hertz. Now after the sampling is being done, again a reconstruction of the signal should also be possible. So if we are to reconstruct x of t from x cap of t, then we should also be able to recover x of omega from x cap of omega. So this recovery is possible if there is no successive overlaps of x of omega. So what we are trying to tell here is, if we pass this spectrum to a low pass filter, then it is possible, if we pass it to a low pass filter, it is possible to retrieve just this x of omega only if there is successive spacing between the spectrums. So this requires that Fs is greater than 2b. Hence it is very clear that this is Fs and this is b. So this Fs should be sufficiently greater than or the minimum condition equal to 2b, so that recovery is possible. Also the sampling interval t equal to 1 by s, and hence we can also write t lesser than 1 by 2b. The gap between the two adjacent spectral repetitions, you can see that the gap between these adjacent repetition is nothing but Fs minus b. So it is given as Fs minus 2b hertz, right? And x of t can be recovered from its samples by passing the sample signal x of t through ideal low pass filter having a bandwidth of any value between b and Fs minus b. So the minimum sampling rate Fs is equal to 2b required to recover x of t from its samples x of t is called as the Nyquist rate for x of t. Hence we have to maintain the sampling, the minimum sampling rate should be maintained as Fs is equal to 2b, where b is nothing but the bandwidth of the input signal, which is represented in hertz. And this minimum sampling rate is called as the Nyquist rate. The corresponding sampling interval t equal to 1 by 2b is called as the Nyquist interval for x of t. The samples of the signal taken at this Nyquist rate are called as the Nyquist samples of the signal. Thank you, students.